So this is an example of doing a full Gaussian elimination procedure just to illustrate the process of Gaussian elimination. So I'm going to use for this example a solution to a problem that is shown on the DC Node Solutions Level 3 example that is also recorded. Now I will point out first of all that Gaussian elimination is not the best way to solve this problem. The best way is to do the process that I showed in that example, which is to do substitution. So for example, since we have some rather simple equations here, we can simply substitute those into the more complicated KCL equations, or the bottom two rows of the simplified equation, or the matrix, either one, and we could solve it that way more easily really than we can do with Gaussian elimination. But just for the sake of completeness, I'm going to show you how to do a full-fledged Gaussian elimination for this problem. So here are the equations. The nodal equations that we want to solve in matrix form. So I've copied those over here, just transcribed them. So we put this into an augmented matrix, as you do for Gaussian elimination. So the matrix of the coefficients that multiply the unknown variables, that becomes the left portion of this. So we just have the 0, 0, 1, 0, negative 1, 0, 0, 1, and so forth here. And then the right-hand portion of this becomes the constants, the 3, 3, negative 5, 2. And that forms what we call an augmented matrix. So instead of the original 4 by 4 matrix, we now have a 5 by 4 augmented matrix. And this is the standard approach to doing Gaussian elimination. Now in Gaussian elimination, there are several things we can do. We can multiply any row, that is the entire row of 5 elements, by a constant, which we don't typically need to do here. Unless you want to do Gauss-Jordan elimination, where you actually go all the way down to the reduced row echelon form. But we're going to do an example of Gaussian elimination here with back substitution, which is probably the more numerically efficient way of doing things, meaning that it takes less computation to do it this way. So we won't need to multiply by a constant, but one thing we do sometimes need to do is to interchange rows, and in fact that'll be required here, so we're allowed to exchange rows. Remember, multiplying by a constant, of course, that's just taking one of these original equations and multiplying it through by a constant, and of course we know from algebra that that's a permissible operation. Rearranging the rows or switching them, that of course just corresponds to changing the order of your equations, which obviously will not have any effect on the solution. The third thing we can do is to add a multiple of any row to another row, and that just corresponds to taking linear combinations of the original equations, which, as we know from elementary algebra, is a permissible thing to do in solving, and again, that will not change the values of the solution variables, the v1, v2, v3, and v4. So we're going to do a row reduction. Now you can also do column reduction, but that's not generally very advantageous, and it has the confusing aspect that then we're going to change the order of the unknown variables if we were to interchange columns in this matrix. So we're going to avoid doing that and just do what we call partial pivoting, which means we're only going to change things in terms of rows, not in columns. And that's the normal, probable way of doing this. So the first thing we have to do is our goal is to make this an upper diagonal matrix, meaning that we're going to have non-zero entries only on the main diagonal, which we call the principal diagonal here, of the left-hand portion. When I say the matrix, I really mean the left-hand portion here. And then we can have non-zero entries above that principal diagonal, but all of these entries down here, this one, this one, this one, this one, this one, and so forth, these all need to be 0. That will give us our that will give us our row echelon form. It's not the reduced form. The reduced row echelon form would have zeros then on the upper diagonal elements as well, and have 1s down the principal diagonal. That would allow us to read the answers directly from this column. But we're just going to use the row echelon form, which is this type of form, where we have only zeros below the principal diagonal. So this is our goal, is to get down to here so we can do the back substitution. So the first thing we're going to need to do here is, because we want to have the elements here on the diagonal be non-zero, is we cannot use this as the uppermost row, because it has a 0 in the first position. So we're going to need to switch rows, and I've indicated here what we're going to do. So I'm going to make this our first row, and then this is going to become our second row, just in an effort to make this look more like it should. And then we're going to use this as our third row, since it has an element here in the third column, and we're going to make this our fourth row. So that is indicated here that I'm going to make first row become R3, the second row become R2, R3 is going to become R1, and R4 is going to become R2. So I've just made all those changes here in one step. You could make them individually, but of course that involves a lot more writing, so it's not really necessary to do that. So now I've basically moved these two rows to the top and these two rows to the bottom. So now we have the proper non-zero element in the position we're working on now, which is this. So now our goal is to try to get the first column to have the proper form, which is non-zero here and then 0 here, here, and here. And we do basically one column at a time, working from left to right in Gaussian elimination. So clearly what we want to do is to add this row to this row, because 0.25 plus minus 0.25 will eliminate this entry. Now if this were not minus 0.25, which it happens to be here, then we would multiply this row by this entry divided by this entry, and then we could subtract that from the second row, and that would do the same thing. So sometimes it's a little bit more complicated than what it happens to be here because of the particular structure of these equations. So in other words, the second row is going to become, in this case, just R1 plus R2. And down here, we're going to do another operation at the same time because it affects a different row, and therefore we are allowed to do these two operations at the same time just to save rewriting. And so we're going to add basically 4 times this row to this one, because that will make this 1 added to -1, of course, will give us 0, which is the desired result down here, is to have all zeros in this row. This one, of course, we don't have to do anything because that already has a 0 there, so we don't need to make any change to row 3. Now, of course, if you did, then you would do a similar type of thing. And basically, so we're going to replace row 4 by 4 times row 1 plus row 4, and that will give us the new desired thing with a leading 0. And in general, of course, what we're really doing is multiplying this times this divided by this, and then subtracting that. So that's equivalent to doing this. Okay, so we now carry out those operations. So adding row 1 to row 2, this of course will give us 0. And then adding this, that's also going to give us a 0 there because those happen to be equal. That won't happen in general, but it did here. And then adding those two, of course, just gives us minus 0.5. Adding those two, because it's 0.6429 minus a negative 0.1429, that will clearly just give us a positive 0.5. And then we do the same thing with the constant. So -5 plus 2 becomes -3. The third row we just recopy because that's unchanged. And then for the fourth row, again, we're adding 4 times this to this. So that'll give us a 0 here, of course. And then doing on a calculator, we multiply 0.3929, or the negative of that rather, times 4, and add it to 0. So that will just give us a minus 1.5716. And then we multiply this times 4, that'll give us -2, add that to 0, gives us a -2. And then the 0.6429 times 4, and then add that to 1. If we do that on a calculator, that works out to be 3.5716. And finally, for the constants, then minus 5 times 4 is -20, plus 3 will, of course, give us -17. So that completes the operation here, and now we have the first column taken care of. So now we need to work on the second column because we still have a non-zero entry here, which we want to get rid of. However, before we can do that, we notice that, well, we have a 0 here, and we want that to be non-zero, and there's nothing, obviously, we can multiply 0 by that's going to make it non-zero. So now we were actually required to switch rows again. So we're going to switch rows 4 and 2, and generally, for purposes of minimizing round off, you want sort of the largest value to go towards the top as a general rule of thumb, but here there's really no choice. So we just interchange row 4 and row 2 and switch those around, including the constants. Remember, the constants always have to, or the right-hand side always has to track what you're doing with the left-hand side. You can't do it to one and not the other, because that would be doing an illegal algebraic operation. So we switch those two, just the ordering of the equations basically. And now we have the desired, well, we already have zeros here. So this column is already good, in fact, once we've made that switch. So now we go to the third column and start working on that. And we want a non-zero entry here. We already have that. Down here, we want to make this 0. So what we're going to do is divide this row by 2 and add it to row 4. So we're going to replace row 4 by row 3 divided by 2 plus row 4. And of course, we always use row 3 here because we don't want to affect these zeros as we would if we started adding combinations of row 1 and row 2 down here. We want to keep those as zeros so we don't disturb those. And again, what we're really doing is we're adding this divided by this times this, and that will basically make that 0. So we carry that out, and the 0.5 here plus negative 0.5 is 0. And here, of course, there's nothing to do since that's 0, so we'll just get row 4 copied down as 0.5. And then we have 3, divide that by 2, that gives us 1.5. Add that to the negative 3, and that will give us negative 1.5. So now we have achieved the desired the desired row echelon form. This is not a reduced row echelon form. That would require zeros on the upper portion of the matrix as well. But we're going to use back substitution now. So what we do here is we're going to start out. Obviously, the easy thing to solve for is the lower equation. So that just says 0.5 V4 is equal to negative 1.5. So that allows us to write directly V4 is negative 1.5 divided by 0.5. And of course, that math we can do in our head. That just gives us negative 3. V3, that's a trivial equation because this is a 1 and there's nothing else to do here, so there's no entry here. So that just says V3 equals 3. So we just write that out. Then to find V2, we go up to the next row. So notice we're going from bottom to top here because that's obviously the easiest way to do because these are zeros. So we go up here now and we'll write that negative 1.5716 V2. We'll put all the other stuff on the right-hand side because we know V3 and V4. So that'll equal to 2V3 minus 0.35716 V4. And then, of course, minus 17, the original constant. And then we simply substitute in those known values for V3, which is negative 3. So that, V3 is 3 rather. So the 2 times 3 gives us 6. And then the minus 3.5716 V4, we put in V4 is negative 3. So that cancels this minus sign, gives us plus 10.715. And then we still subtract 17. And now we just add that up on a calculator. And we get a negative 0.285. Now notice there is quite a bit of round-off error there, or I'm sorry, quite a bit of cancellation, I should say, which can lead to round-off error because when we add these numbers, they're almost canceling out and giving us a rather small remainder. So we have to make sure that we have adequate numbers of digits on these numbers, that the round-off error will not harm that calculation. And that's just a general thing when you're doing algebra. You want to watch out for issues of round-off error. And so then we can just divide both sides of this equation now by the negative 1.5716 to get V2. So this constant divided by that then just gives us, on a calculator, 0.181 volts. So that finds V2. And then finally we go up to the top row to find V1. And so that equation can be written as 0.25 V1. And then we bring everything else over to the right-hand side because we know V2, V3, and V4 now. So we'll have plus 0.3929 V2, plus 0.5 V3, minus 0.6429 V4, and then we, of course, have the original negative 5 that was already on the right-hand side. And then we just substitute in the known values now of V2, V3, and V4. So putting in the V2 that we just calculated as 0.181, putting in V3 that we calculated as being 3, and put in the V4 that we calculated as negative 3 up here, and then of course still have the minus 5, and so now we just enter that expression on a calculator, and that turns out to be negative 1.5, some trailing zeros, and then just dividing by the 0.25, we can easily see that that will be negative 6 for the answer of V1. And these answers are not quite exact because we did have some round-off error occur in this calculation, but they're close enough that those will be accepted in Circuit Tutor. So again, this just emphasizes the need to make sure you carry through enough digits that you will have an accurate answer, particularly if you have any cancellation, as we did here. So that basically completes the back substitution, and that illustrates the process of Gaussian elimination in a relatively complicated case.